Yeah.
Yeah, cool. So let us start. Thank you, everybody, for coming to this new session of the one-word probability seminar. We have the pleasure to have with us Cyril Labbé and Laure Dumaz. We will start with Cyril Labbé, who is now at Université Paris-Cité, recently named university. And they will talk about some aspect of the Anderson Hamiltonian with white noise.
Yeah, thank you very much. Thank you very much for the introduction and for the invitation. Yeah, so I will present the first part of this joint talk, and so together with Laure, we would like to give to present some aspects of the Anderson Hamiltonian with white noise. And most of the results that we will present will be in dimension 1, but I will start the presentation by considering a general dimension, and I will make comment on higher dimension later on. So this first talk will be basically split into 3 parts, and actually they are almost independent. So if at some point you can't follow anymore, you can hopefully follow the subsequent parts. So let me start with the definition. So that's a random operator that we are interested in, which is minus a continuous Laplacian applied to a function f plus a random object psi multiplied by the same function f. So here the function f is a function from Rd into R. At some point in the talk, we will also need to consider the finite volume version where the operator acts on function on a bounded domain. So a domain of side length L in dimension D, and the operator will be endowed with Dirichlet boundary condition, although this doesn't play much role for the result. So here there is this random object psi that I didn't define, and as you can guess, we aim for a Gaussian white noise on Rd. Okay, so Gaussian white noise is not a function; it's a distribution. It's a random distribution, and in particular in dimension 1, you can obtain it as the derivative in the sense of distribution of a Brownian motion. Okay, so this operator, at least formally, I will come back to the rigorous definition of this operator later on, but at least informally, this operator, it is a random Schrödinger operator in the continuum. And one motivation for studying such an operator comes from the topic of Anderson localization. So let me give a very brief account on what Anderson localization is. So it was introduced by the physicist Anderson in the 50s, who proposed to model the Hamiltonian of a quantum particle and a crystal by this random operator. So the discrete Laplacian minus delta plus a random potential V, a random object V. So think of a collection of IID random variables on ZD. And so the lattice ZD here should be thought of as the atoms of the crystal. Okay, and basically Anderson said that if you want to model in real life a crystal, you need to take into account some defects or impurity that the crystal has in practice. And he proposed to model these impurities or defects with a random potential V, so a collection of random variable Vk indexed by the sides of the lattice. And so what he observed was that without these impurities, the spectrum of the operator, so the spectrum of the Laplacian, is absolutely continuous. Okay, you don't have genuine eigenvalues in the sense that the eigenfunctions are not in L2, they are signed on the whole ZD, which are not square integrable. And the spectrum is, of course, deterministic and absolutely continuous. And what he observed was that if you add this random potential V, then you will change drastically part of this spectrum. And in particular, the bottom of the spectrum will become pure point. You're going to get genuine eigenvalues with square integrable eigenfunction. And it's even more than that. The eigenfunction will be not only in L2, but actually will decay exponentially fast. Okay, and that phenomenon is referred to as Anderson localization. And so it gave rise to a large literature. And to summarize very briefly the main results, so in any dimension, it was proven under some assumptions on the potential, I'm not giving any details, but that indeed the bottom of the spectrum satisfies this Anderson localization. And in the specific case of dimension 1, actually it was proven that not only the bottom, but the whole spectrum satisfies Anderson localization. Okay, and there are also results for in the continuum, but not with the white noise. And as you can see, white noise is a natural continuum counterpart of IID discrete models because it arises at a scaling limit. So in particular, it shares with IID discrete potentials this independence property. So it's very convenient, but at the same time, it's very irregular. Okay, so it was not so much considered so far in the literature. Okay, so that was a slide of introduction to the topic. And now I will present some aspects of this operator H and its finite volume version HL. So in this first talk, I will present three parts. The first part about this infinite volume operator in dimension 1. Then I will move to properties of the finite volume version of the operator, still in dimension 1, but in the limit where the size L of the box goes to infinity. And finally, I will address issues of regularity that are coming from the white noise. So white noise is very irregular, and therefore the definition of the operator is unclear. Okay, so there are some issues there, which are mostly analytical. So the arguments are PDE or functional analysis, but I don't want to start with this aspect. So for the moment, let's assume that the operator is well defined, and we'll see at the end of the talk what the issues are. Okay, so let me start with the infinite volume operator, and it's a good opportunity here to illustrate what I presented before about Anderson localization, because actually the first result that I will present is a result of Anderson localization for this operator in dimension 1. Okay, so I recall here the operator, and the result that we obtained with Laure is the following. So almost surely, the operator H is self-adjoint on L2, actually on a subdomain, on a dense domain of L2, and I will come back to that at the end of the talk. The spectrum is pure point, so you only have genuine eigenvalues with L2 integrable eigenfunctions. The eigenvalues are dense in R, so you have a random countable collection of points in R, which is dense. And the eigenfunctions decay exponentially fast. Okay, and more precisely, what does this exponential decay mean? It means that if you look at the eigenfunction phi lambda associated to some eigenvalue lambda, then, well, this sort of Euclidean norm of phi lambda and phi prime lambda decays exponentially fast at infinity. And the rate of decay is deterministic. Okay, it's a constant gamma lambda, which is a deterministic function of lambda. Okay, it's actually explicit, and I will come back to this quantity in the next slide. This quantity is called the Lyapunov exponent, and I would like to say a few words about the Lyapunov exponent. So you could be a bit surprised that we don't only consider phi, but also phi prime. But the reason can be explained pretty easily. So if I draw the the eigenfunction phi lambda. So typically the eigenfunction phi lambda for some eigenvalue lambda, it has infinitely many zeros. Okay, it oscillates on R, so it has infinitely many zeros, and the exponential decay can be observed if you look at the absolute value of this function and you look at the way at the decay of the successive peaks of these absolute values. Okay, and now if you sum up phi lambda and phi prime lambda, then you don't have any zeros anymore, and you can hope for this sum of the square to converge, or at least the log to converge to some constant. Okay. Anyway, so one should think of this eigenfunction as being a function that oscillates and decay exponentially fast at infinity. So I should say that this result is expected because the literature on Anderson localization, as I said before, well, shows that in some degree of generality, in dimension one, the whole spectrum is pure points. But here we are considering a noise which is quite irregular, and it doesn't, and so the general results don't apply to this operator.
Honestly, there is a question in the chat.
Yeah, sorry.
Whether there are some results when phi is a smooth Gaussian potential.
Yeah, so there are some results in that case. So there are results in general dimension when there is with a smooth Gaussian potential for the bottom of the spectrum. And then in dimension one, there are some general results provided that the Gaussian potential is not too large at infinities. Okay, so what I can say is basically for smooth Gaussian potentials in dimension one, the result is probably not written in full details, but people would tend to think that, okay, it's in the closure of the literature. Now, for Gaussian white noise, there are some issues that needs to be dealt with first. Okay.
Thank you.
Okay. So I don't want to say more, to say anything about the proof of this result, but I would like to say a few words about this Lyapunov exponent and to say where it comes from. Okay, because I think it could illustrate the reason why we have exponential decay here. So if we look at this ODE, so minus y, the second derivative of y plus y times psi is equal to lambda y for some fixed parameter lambda. So this ODE is nothing but the eigen problem associated to the operator. Okay, so an eigenfunction needs to be a solution of this ODE, which is square integrable. So it's natural to study this ODE for some fixed parameter lambda. So of course, the space of solution is two-dimensional, and you can parameterize this space of solutions by picking two particular solutions, the so-called Neumann and Dirichlet solutions. And Neumann and Dirichlet refer to the boundary or initial condition that you impose, for instance, at time 0. Okay, so 0 is arbitrary here, but for simplicity, let's take 0. And so we impose these Neumann and Dirichlet boundary conditions to yn and yd, and then any solution is a linear combination of these two particular solutions. Fine. And then it's natural to introduce the so-called propagator. So the propagator at time t, it's a 2x2 matrix in which whose columns are the function and first derivative of the Neumann and Dirichlet boundary solutions. Okay, so it's a 2x2 matrix which happens to be invertible at all times. Okay, it's a property of these solutions, and it evolves with time. And now let's observe the following. So there is a flow property. So if you want to evaluate this matrix at time t, you can first compute the matrix at time s, and then compose with the matrix PST that I didn't define, but whose definition you can guess. I think it's basically the same propagator, except that the Neumann and Dirichlet solution are defined by imposing these two initial condition at time s instead of time 0. Okay. Now observe that since we are dealing with a white noise, and given the independence properties of the white noise, these two matrices are independent. Okay, so we are taking the product of two independent matrices because they depend on the white noise on two disjoint regions of R. And so, for instance, if you evaluate your matrix at time n for some integer n, you can view it as a product of n IID matrices. Okay? And then we fall into the scope of general results on the asymptotic behavior of product of random matrices. Okay, and there are general results from the 70s that say that if you look at the norm of the matrix, okay, whatever norm you choose doesn't really, it doesn't matter. Well, the norm of the matrix grows exponentially in time. It's a theorem due to Furstenberg and Kirsten. And the rate of growth is a deterministic constant gamma lambda, which happens to be positive. Okay? And this constant is called the Lyapunov exponent of this evolving matrix. And actually, this constant gamma lambda, which is deterministic, only depends on lambda, well, it's somehow explicit because it is given by the so-called Furstenberg formula, which in the particular case of white noise can be computed explicitly. And you get, so for fun, I wrote the precise expression, but just to say that you can make explicit computation on this exponent, Lyapunov exponent. Okay, and now another point that can be said is that actually you can say much more about the solution of the ODE. Okay, so recall that P lambda t, if you apply P lambda t to some vector of R2, you get the solution and its derivative of the ODE that I wrote here. Okay, so you get the solution of this ODE for some initial conditions that you impose at time 0. Okay, and it happens that almost surely, this is Osseledek's theorem, there exists a random direction of R2 in which, if you compute your solution, P lambda t starting from this initial condition U lambda, well, the norm doesn't grow exponentially fast. It actually decays exponentially fast at the very same rate gamma lambda. And on the other hand, if you look at any other direction of R2, the solution grows exponentially fast at rate gamma lambda. Okay, so there is a quite surprising splitting like this that say that there is one particular direction where you have exponential decay, and in other direction you have exponential growth. And so just to give some ideas about this Anderson localization business, here you could guess that the eigenvalues, eigenfunctions will be those lambdas for which you can find the same direction towards plus infinity and minus infinity, where you have exponential decay. Okay, so a priori, the direction towards plus infinity and minus infinity are not the same, they are actually independent. And if you want to have a square integrable function solution, you need these two random directions to be the same. Okay, so just to give some flavor of what is needed to get this Anderson localization. Okay, so that's all what I wanted to say about H in 1D. So let me move to the finite volume operator. And if you didn't really follow what I said about Lyapunov exponent, it will not be used anymore in this part. So what we saw that the operator in the infinite volume operator in 1D satisfies this Anderson localization property. And then we could think that the finite volume operator in the large volume limit, well, should not display anything special, okay? Of course, this finite volume operator converges in some sense to the infinite volume operator. So you could say, well, everything is said on this operator, given that what we saw on H. And I will we will try with Laure to convince you that it's not the case, that many more things can be said about HL in dimension 1 in the large volume limit. So let me recall the definition. So we have this random operator on a finite segment of length L. So it happens that this operator is self-adjoint with discrete spectrum bounded below. Okay, so you have the smallest eigenvalue, then the second smallest, etc. And this sequence, this random sequence of eigenvalues, it converges to plus infinity. Okay, the sequence converges for any given L. And I think it would be, it's good to think of this spectrum of these eigenvalues as a sort of perturbation of the eigenvalues of minus Laplacian. Okay, so if you disregard the noise, you get simply the opposite of the Laplacian on a segment. You can compute explicitly the eigenvalues, and they are all positive. And now when you add the noise, you perturb these points randomly. Okay, and so typically with large probability, the smallest eigenvalue, which used to be positive in the unperturbed case, becomes negative with positive probability. Okay, so you have a perturbation. So actually the behavior of this first eigenvalue in the large volume limit was studied by McKean in the 90s. And here is the result that he showed. So McKean showed that you can identify a deterministic function of L, AL, that behaves logarithmically. And he showed that at first order, the first eigenvalue, lambda 1L, when L becomes large, at first order, it behaves like minus AL. So it diverges to minus infinity like minus this logarithm. And then he showed that the fluctuation around this first order asymptotic is actually tiny. So the fluctuation are of order 1 over square root of AL. So tiny fluctuation around this first order. And the asymptotic law is a Gumbel law. Okay.
Sorry, Cyril, I got lost. What was AL?
Yeah, AL is written here. So AL is a deterministic function that McKean introduced. So there is a more formal definition, but it's a deterministic function of L, which dictates the asymptotic behavior of lambda 1L. Okay, so basically when L becomes large, lambda 1L at first order is deterministic. It's a sort of law of large numbers. It's given by minus AL, and then the fluctuations are of order 1 over square root of AL around some Gumbel law asymptotically. Okay, so it's a deterministic quantity. Fine. So the first question that we investigated with Laure, that was the starting point, was to try to extend this result of McKean to other eigenvalues, so not only the first one, but the case one for some fixed k. And then we wanted to understand also the joint law of these smallest eigenvalues and possibly also the behavior of the corresponding eigenfunctions. Okay, so do the eigenfunctions look like something very much localized, or are they delocalized as the eigenfunction of the Laplacian in everything in the limit L goes to infinity? So to enter the question, to state the result, I need to introduce this point process of eigenvalues. So you look at this random point process. Okay, you associate to any eigenvalue a Dirac mass, and you rescale every eigenvalue in the same way as McKean. Okay, because you basically what you want to do, you zoom in at the bottom of the spectrum of the operator, and you apply a zoom, a rescaling, which is such that intuitively the spacing in between two consecutive eigenvalue becomes of order 1. Okay, so you hope that this scaling is the right one. Actually, there are arguments that indicate that this is the right one. But anyway, so you apply some scaling and you hope that within the scaling, the spacings become of order 1 at the bottom of the spectrum. Another quantity that I need to introduce is, well, some sort of candidate for the point where the eigenfunction, the kth eigenfunction phi kl, could be localized. Okay, so if ever phi kl happens to be localized, the best guess that you could give for the localization center would be the point where the maximum is achieved. Okay, so I call this point UKL. So it's a point in minus L/2, L/2. And I recall that AL was a deterministic quantity introduced by McKean that goes to infinity like a log. So here is the first result that we obtained with Laure. So we showed that the point process of eigenvalues converges to a Poisson point process of intensity e to the lambda d lambda. Okay, so within this rescaling, indeed, we observe in the limit a nice point process with a spacing in between two consecutive points, which is of order 1. And regarding the eigenvalues, the eigenfunctions, sorry, we showed that whatever rank k, so if you fix k, and you look at the kth eigenfunction, if you recenter this eigenfunction near its maximum, UKL, and if you look at this random function in a tiny region around UKL, so a region of order 1 over square root of AL, okay, a tiny region near the maximum. And if you apply an appropriate L2 scaling, so phi KL is normalized in L2, it's an eigenfunction which is normalized in L2. So it's natural to apply some L2 scaling here. Well, what we showed is that this random function converges in probability to a deterministic function, which is explicit, the inverse of a hyperbolic cosine. And this deterministic function is the same for every rank k. So whatever k is, you get the same function. I will illustrate this result in the next slide. So let me make a comment. The first convergence is coherent with McKean's result, because if you compute the law of the first point, there is a first point from the left. Of course, there are infinitely many points to the right in such a point process, but you can compute the law of the first point coming from the left, and it follows a Gumbel law. Actually, the opposite of a Gumbel law, because there was a minus in McKean's result. So it's coherent with McKean's result. Okay, so let me illustrate this convergence a little bit on the next slide. So if you draw very roughly the first eigenfunction, phi1L, when L becomes large, what you see? Well, you see the following. You see a point U1L, which is random. Ah, yeah, it's on 0L. Actually, it should be on minus L/2, L/2, sorry. So you see a random point here. And I didn't state it in the last slide, but actually this point asymptotically is uniform. But anyway, you see a random point here, and you see a function which is very much localized. Okay, so most of its L2 mass is in a tiny region around U1L, and the shape that you observe here, after some appropriate scaling, is the inverse of a hyperbolic cosine. Okay. So you see a deterministic shape in the scaling limit. And now if you look at the fifth eigenfunction, for instance, well, you see the same behavior around its maximum U phi L, the argument of its maximum. You also see the inverse of a hyperbolic cosine. And actually, you can say much more about the behavior of this eigenfunction near the localization centers of previous eigenfunctions. So I won't get into the details for now, but many more things can be said about these eigenfunctions. Okay, so what did we see? We saw that at the bottom of the spectrum of HL, we have a very strong localization property. Okay, so the eigenfunctions are very much localized in tiny regions of the interval of length L when L becomes infinite. And actually with Laure, we then try to get a similar result, or at least to investigate the rest of the spectrum, not only the bottom of the spectrum of HL, but other regions of the spectrum. And actually, we came up with a sort of classification of the possible behavior that can be observed. Okay, so we identified 5 regimes, and these 5 regimes are ordered by increasing energy. Okay, so we either look at the bottom of the spectrum, so we zoom around some energy level E, which is minus AL, so this quantity is minus AL, and then we are back into the regime that we just looked at the previous slide. But we also looked at other regime where the energy is of order 1 or even higher. Okay, so we identify 5 regimes, and for these 5 regimes, we have a complete understanding of the local behavior of the eigenvalues and the behavior of the eigenfunctions. Okay, so let me start with the eigenvalues. So I will not give precisely the rescaling, but you should keep in mind what I presented before. So before I said you look at the point process of eigenvalues under some rescaling. So of course, the rescaling depends on the region of the spectrum you want to look at. So I gave the detail for the bottom, but a similar rescaling can be applied in the bulk, crossover, etc. So I won't give the precise rescaling. But in any case, it's a rescaling under which locally around this energy E, you see a spacing between the consecutive eigenvalue, which becomes of order 1. Okay, so you zoomed in within the spectrum. So we see a Poisson point process in the first 3 regimes. And the intensity of this Poisson point process is explicit. Okay, so e to the lambda in the bottom and constant higher within the spectrum. On the other hand, if we look at the top of the spectrum, so very high energies, what we see that the local statistics becomes completely deterministic at first order. Okay, so at first order, the spectrum, the eigenvalues are essentially the same as those eigenvalues of minus Laplacian in the same energy level. Okay, so at first order, it means that the white noise doesn't have any impact on the eigenvalues locally in these high energies. And then in between these two Poisson regime and Picket-Fence regime, we identify a regime that we call critical, where the point process of eigenvalues converges to a random point process, which is called SCH, that is not deterministic. It's a random point process that interpolates between a Poisson point process and these deterministic Picket-Fence statistics. And actually, this point process was introduced before by Krzyzewski, Walko, and Dirac in some studies of random matrix models. And maybe Laure will mention that in her talk. Okay, now what about the eigenfunctions? Well, for the eigenfunctions, we observe 2 phases. We observe a localized phase in the same region as the Poisson phase. And what do I mean by localized? I mean, you look at the eigenfunctions that corresponds to the eigenvalues that you are considering in each regime. And these eigenfunctions are normalized in L2, and you ask yourself, does the L2 mass concentrate in a tiny region of the segment when the segment goes to infinity? Or is this L2 mass spread out on the whole segment when the segment goes to infinity? So for instance, if you have a sine, the eigenfunction of the Laplacian, you don't have a concentration of the mass is completely spread out. On the other hand, in the bottom of the spectrum, we saw that the eigenfunctions are very much concentrated. So basically, we have this concentration phenomenon for the first 3 regimes, and we have a delocalization phenomenon higher within the spectrum. And the length of localization is explicit. So we already saw that in the bottom of the spectrum, it's of order 1 over square root of AL. So this is exactly 1 over square root of AL. And if we get higher within the spectrum, we see that the localization length is larger and larger. Okay, so somehow the higher you look at within the spectrum, the less localized the eigenfunction is. And you see that in the crossover regime, you have an unbounded localization length, but it's still negligible compared to L due to the assumption E smaller than L. And then higher within the spectrum, you see a delocalized eigenfunction. And finally, let me mention that you can also give very precise information about the behavior of the eigenfunction. So not only in the bottom, where we saw that the shape is deterministic, it's the inverse of a hyperbolic cosine, actually in the other regimes, you can give very precise information. So I didn't write everything because, for instance, in the bulk, the details would be a bit long to write and not so informative. But what is the most interesting, I think, is this two-regime crossover and critical, where actually the eigenfunction is oscillating very much. So you have very strong oscillations, okay? And somehow, if you are able to remove these wild oscillations, then you can see a sort of explicit shape, which is random, and which is this function, the exponential of some two-sided Brownian motion minus some drift. Okay, and Laure will state something very precise in her talk. She will come back to this point. But I just wanted to mention that we have a sort of surprising behavior. So in both the localized regime, which is the crossover regime, and also in the delocalized regime, which is the critical regime, we observe the same universal shape. And this universal shape actually appeared in a result of Rifkin and Dirac, still for random matrix models.
May I also ask one question?
Yes.
Thank you. What exactly is L and how do you determine it?
So L is the length. L is the length of the segment where you consider your operator. So you restrict your operator to some segment of length L. It's a fixed quantity. Mm-hmm. You study the spectrum, etc., and then you look at the behavior when L goes to infinity. Okay, so it's just a deterministic parameter, which is the volume of the underlying box.
Okay, thanks.
Right.
Sorry, and this in random regime, B of T is Brownian motion, or what is it?
Yeah, it is a Brownian motion. So B of T is a two-sided Brownian motion.
Okay, but in that sense, how it's possible that this function is delocalized, exponentially decay in T, yes?
Yeah, so okay, very good question. So actually, here I didn't explain the scaling.
Mm-hmm.
Okay, so you have to apply a rescaling. So to observe this shape in the crossover regime, you have to look at your eigenfunction at a spatial scale of order E. Mm. And if you look at your eigenfunction at a spatial scale of order E, you observe this eigenfunction, this shape. Okay.
Thank you.
But E is negligible compared to L. So if you follow this, you see this function, if you go to at plus infinity or minus infinity, you have an exponential decay. And this explains why at scale E, it's still localized. On the other hand, for the critical, the scale is L, and so you don't see localization. So Laure will give many more details on this aspect. And actually, there is also, we can also prove, actually we proved a convergence at the operator level. So we didn't only prove convergence of the eigenvalue eigenfunctions. And Laure will, in her talk, she will explain this convergence at the operator level and the connection with result of Falco and Dirac. Okay, so just let me mention that the crossover regime technically was definitely the most involved one. So it took us quite some time to prove this result. And in particular, if you remember what I said about the Lyapunov exponent, there is also an invariant measure for the direction in R in R2, sorry, an invariant measure that you need to exploit extensively in this business. And in the regime, in the crossover regime, this caused many difficulties, and that's why this is probably the main result in that respect.
Thank you.
So that's all for HL in dimension 1. And let me move to the last part on the construction of the operator. So I think I still have about 5 minutes. Okay, so I said the operator.
I think even more than 5 minutes.
Okay, okay.
I'm not.
So I said the operator is not easy to define because white noise is distribution valued. So let me explain a little bit more why the fact that white noise is irregular causes difficulties for defining H. Okay, and when you want to define such an operator, you want to define a domain of functions in L2 on which your operator applies and on which your operator is self-adjoint. And with white noise, we'll see that an immediate difficulty arises. So usually what you do, you start by applying your operator on smooth functions, and then you try to extend the class of function that you consider. You take a closure, and then you impose boundary conditions. So the first operation is to consider smooth functions. But the thing is that if you start with a smooth function, a C-infinity function, and you apply your operator, you have two terms. You have the Laplacian of the function, which remains smooth. But on the other hand, you have the product of your function with white noise. And it happened that white noise is irregular everywhere. Okay? And this product is well defined, but it doesn't belong to L2. It remains a distribution everywhere. Okay, so this is never in L2, and therefore the sum of these two terms cannot be in L2, whatever function f, whatever smooth function you consider. And consequently, any smooth function cannot be in the domain of your operator if the domain exists. Okay. And actually, this little discussion gives some ideas on the behavior that functions in the domain should have. Okay, if you want f to be in the domain, you actually need something specific to happen. If you want f to be in the domain, of course, you need Laplacian f plus f times psi to belong to L2. Okay. But as we saw that f times psi is not in L2. So if you want the sum to be in L2, you need Laplacian f not to be in L2 either. Okay, you need Laplacian f to be irregular, to be a distribution that compensates for the irregularity of f times psi. And then you should hope that the compensation is such that the sum is in L2. And then if you, heuristic argument shows that locally, you should expect that Laplacian f is essentially like psi. Okay, it behaves like the white noise locally. So basically, f should be locally like the inverse of the Laplacian applied to psi. And this is not a very regular function. It's a function which at most is Hölder 2 minus d over 2. Okay, because of regularity properties of the Laplacian. Okay, so what do we see? We see that the domain is made of should be made of random functions with low regularity. And actually, it's even worse than that.
Sorry, what is 2 minus d over 2 minus, again, minus? What is it?
Okay, it's not
plus minus.
I agree. So it forget the second minus.
Okay.
So basically, psi has regularity minus d over 2. Actually, slightly less than minus d over 2. And when you apply the inverse of the Laplacian, you improve regularity by 2. So the regularity of f is 2 plus the regularity of psi, which happens to be minus d/2, and actually slightly less than minus d/2. So it's 2 minus d/2 minus epsilon for any given positive epsilon. So it's not, yeah, I should have written that more formally. Okay, so it's slightly below 2 minus d/2. So for instance, if you think of the 1D case, you're gonna get something slightly below 3/2. Fine. And as I said, there is another difficulty that arises and that you can identify thanks to this discussion. So if you believe that a function in the domain should behave like minus Laplacian inverse applied to psi, then if you apply your operator to such a function, you're going to see the product of minus Laplacian, the inverse of minus Laplacian of psi times psi. Okay, you should see this quantity arise whenever you apply your operator to such an f. And it happens that Gaussian computations show that in dimension 2 and higher, this quantity blows up. Okay, so in dimension 1, this quantity is well defined, but in dimension 2 and higher, this quantity blows up. So what is the conclusion of this heuristic discussion? First, the domain, if it exists, should be made of random functions with low regularity. And second, in dimension higher or equal to 2, you need some renormalization of the operator to compensate for divergences. Okay, so let me, okay. I have maybe 2 slides. So one slide about the construction, some ideas about the construction in 1D, and a second slide about higher dimension. So in 1D, how can you rigorously construct the operator? So how can we implement this heuristic idea that the function should behave like this inverse of the Laplacian applied to psi? So to understand a little bit how the construction works, let me come back to the smoother setting where instead of psi, you have a smooth noise. So if you have a smooth noise, function v, which is in L1 log, for instance, the construction of this operator can be achieved by the theory of Sturm-Liouville. Okay? So it's a well-understood theory that allows to build actually an even larger class of operator. And for smooth enough noise, for noise in L1 log, what you have that the domain, thanks to the theory of Sturm-Liouville, is made of these functions in L2, which are absolutely continuous, whose derivative is also absolutely continuous, and which are such that this differential expression belongs to L2, and in addition, function f that satisfies some boundary conditions if you are on a bounded domain in space, or satisfies some growth condition if you are in an infinite domain. Okay, but in any case, the domain in the smooth case is made of functions which are twice differentiable, okay, in that sense, and for which the sum belongs to L2. And as I explained in the previous slide, this is not possible anymore in the white noise case because functions in the domain are not twice differentiable. Okay, functions in the domain are Hölder 3/2 at most in dimension 1, and therefore there is no second derivative. Okay, so in the white noise case, this standard theory cannot apply. But actually, with Laure, we learned that there is a generalization of the Sturm-Liouville theory that allows to take care of more singular noises like white noise. And the observation is the following. If you start from this differential expression involving white noise, you can rewrite it in the following form, where B is the integral of psi. So B is a Brownian motion. So it's just an integration by parts, and you see that, you can rewrite this expression in that form. So a priori, you could say there is no, it's not necessarily interesting, and there are many other ways of rewriting the expression. But actually, that's the correct approach, because what you need to impose, you need not to impose that f prime is absolutely continuous. You need to impose that f prime minus bf. So you remove to f prime something which is not differentiable, is absolutely continuous. Okay, so it's completely consistent with the discussion on the previous slides, where we saw that locally f should behave like this inverse of the Laplacian applied to psi. And this is exactly what is meant by removing to f prime something irregular. And indeed, it happened that you can prove that there is a dense collection of functions that satisfies this, and then the whole theory of Sturm-Liouville can be applied, and it allows to build the operator. Okay, so you have to twist the notion of derivative in some sense.
Sorry, and B is the Brownian motion, yes?
Exactly, so B is the integral of psi.
Yes, so it's the Brownian motion.
Yeah, it's a Brownian motion, exactly.
But
the construction here is completely deterministic. You apply the theory for any realization of the Brownian motion.
Thank you.
Okay, so last slide. So I'm not giving any other detail on the construction in dimension 1. I would just like to say a few words about higher dimension. So I said in higher dimension, there is a divergence that comes from this product that blows up. And actually, this type of difficulties is encountered in stochastic PDEs and was actually addressed by the theories of regularity structures by Hairer and the paracontrolled calculus by Gubinelli, Imkela, and Perkowski. So their theories apply to parabolic PDEs, but you can also apply them to elliptic PDEs like this operator. And in both cases, you have to identify renormalization constants, which are infinite. And you have to build the operator by some limiting procedure, or build the stochastic PDE by some limiting procedure. So just to give the flavor of the construction, the idea is to start from some regular noise. So you don't start with the white noise, you start from a smoothed out noise, psi epsilon, which is obtained by convolving psi, for instance, with an approximation of a Dirac delta. Okay, so if you smooth out the noise, you don't have any issues anymore of terms that blow up. Okay, but of course, when you pass to the limit on the regularization, if you pass the limit on epsilon, you recover psi, and then you have some blows up. So the idea is to shift the operator by an appropriate constant, C epsilon, which is explicit. So you identify the right constant. This constant actually diverges with epsilon, but you can prove that the sequence of operator converges to a well-defined operator. Okay, so informally, it means that the meaning that you give to this operator in dimension 2 and 3 is that one. You shift the operator by some infinite constant. So this was applied. The first construction was given by Ale and Schuck in 2015 on a torus in dimension 2. And then there were some extensions to dimension 3, other boundary conditions, manifold, in a few papers. Okay. But in any case, in all this construction, they work in finite volume, and you have to apply this idea of renormalization by diverging constant C epsilon. Okay, so I think it's a good place to stop, and I thank you for your attention.
Thank you very much, Cyril. So are there any questions?
Sorry, can't you show once more the construction in one dimension?
Yes.
Yes, in one dimension. So here, psi is not necessary. Not necessary bound. But why? Okay. But why this absolutely f prime minus bf is absolutely continuous, but bf prime is also simply is L2 have to be bf
Yes.
prime have to be in L2. Yes.
Exactly. It has to be in L2.
And you say this construction works not only for white noise, but for some class of random potential, no, not random, even singular potentials. Yes.
Yeah, so actually you're perfectly right. So here we see that it's completely deterministic, and the only requirement is that the integral of psi is well, it's in L2 basically. Okay.
Okay. Thank you. Thank you.
Okay, so you just need the integral of psi to be regular enough. So it works for a large class of distributions. And actually, this theory of this generalized theory of Sturm-Liouville that we learned with Laure in a book by Weidmann was developed in a completely deterministic setting, and it doesn't mention white noise at all. It was definitely not a motivation for him.
Thank you.
Are there any other questions?
Hi, could you go back to the slides of the Lyapunov exponent?
Yes. Let me move this. Here.
Yeah, so here you mentioned this product of ID random matrix. So I'm assuming that there's a result of central limit theory for this log of the norm of this matrix, right? If you center the log, then divide by square root t, that should convert to a Gaussian, I guess.
Yeah, so probably. I don't know much about that. Yeah.
But, okay. So my question is just whether this kind of central limit theory has anything to do with the spectral property of your operator.
Okay, it's an interesting question. Yeah, I'm not an expert of that. Yeah, I can't answer the question.
Okay, thanks.
But yeah, it's a very good question. I think it's what is, there are works in that direction, but I'm not able to answer precisely now. Yeah.
Okay, thank you.
About the spectral properties, yeah, it will give information about the fluctuation of the eigenfunctions, probably.
Okay, thanks for the nice talking.
Thank you.
So are there any other questions? So I was wondering what happened when it is not Gaussian white noise, but somehow Levy white noise. When you have some kind of Levy white noise.
Ah, Levy white noise. Yeah, so so in terms of construction, you will encounter similar issues. So probably in 1D, you can still apply the theory that I mentioned. In higher dimension, no, in higher dimension, it will be another business to deal with Levy. Now, in terms of spectral properties, well, for at least for a sort of Poisson noise, there are results. There are no results like classification of the behaviors, but there are results about localization on the whole on the line, and probably also for local statistics like Poisson in the bulk. But now for more general Levy noise, I don't think it was so much looked at, and definitely not in higher dimension. So it would be maybe 1D.
Thank you. So if there are no further questions, I propose that we unmute ourselves and we thank Cyril for his talk.
Thank you very much.
And we are now going to have the pleasure to have, like, in 2 minutes, Laure with us. So just enough time to get a little bit of coffee or water. Laure, are you there?
Okay, I can share the slides in the meantime.
Yes, that's a good idea. So Laure, are you around? Yeah, there you are. Okay.
Okay, can you hear me and see the slides?
Yes, perfectly. So maybe it's a good time to start, so we don't. Okay, everything looks good. Like to match. So welcome everybody from this short break. We have the second talk of this morning or afternoon, depending where you are. We have with us Laure Dumaz from the CNRS, and now I learned she's in École d'Armement Supérieur. She will talk again about this Anderson Hamiltonian with white noise.
Yes, so thank you very much for the invitation. I'm very happy to present our works with Cyril. And so indeed, that's a follow-up of his talk. But I will still recall everything. So you don't have, so if you just arrived or you were a bit lost, I will recall everything you need to follow my talk. So we study Schrödinger operators, and in this talk we will only talk about the one-dimensional case. A Schrödinger operator is a differential operator, which writes in this way. So it takes a very simple form. It's to a function u, it associates minus the Laplacian of u plus a multiplication by a function v here. And V is called the potential because if you look at the physics literature, this modelizes an electron in a crystal. And if the crystal has some impurities, then they are modelized by this function V here. But for a mathematical point of view, it's not so important, this electron interpretation. And we can see this only as an interpolation between the Laplacian or minus the Laplacian and the multiplication by the potential V, which has they have very different spectral properties, those two operators. And so you can wonder what's happening for the addition of those two. And we will focus on the case where V is the white noise, as in the talk of Cyril. And also in the case where we start from a finite segment. So a function is in L2 of minus L over 2, L over 2. So we start, so our function starts from a segment of size n. And the size of the segment is important, and so that's why we denote these operators as HN to emphasize the dependence in the parameter L. And we put some Dirichlet boundary conditions, but that's not so important. We could change it to other boundary conditions. And let me just recall you why we study this operator. So why the white noise? The advantages of the white noise is that it's natural because it arises at the scaling limit of many discrete models, which has some independence properties. So in this point of view, it's natural to study directly the continuum limit. It's also explicit, so you can make computations. So from this point of view, it's quite nice. And it has nice properties, so the independence properties, which is very important, but also scaling properties and everything you want to. So it's very convenient from this point of view. But there is a drawback that it's irregular. But Cyril told you about this point and told you how to deal with this irregularity. And the goal is to study the spectrum in the large L limit. So we look at both the eigenvalues and the eigenvectors. And in fact, we'll be interested in microscopic properties of the eigenvalues. Namely, we will choose an energy E that may depend on the size and will depend on the size of the system L. And then we zoom, so our eigenvalues, we have a self-adjoint operator, so, and it's discrete. So it's simply, we can see the set of eigenvalues as a random point process on the real line. But now we take a point E and we zoom around this point E. So we look at the points of our point process, which are near this energy E. And when I say near the, so we look in fact at only a finite number of eigenvalues around the energy E. So we zoom really around this point E. So we look at those eigenvalues, and in this side, we look at the associated eigenvectors. So what do they look like? We know it's a random function starting and ending at 0 because we put Dirichlet boundary conditions, but then we can wonder what's the shape of the eigenvector. It's a random function. And usually for random operators with discrete spectrum like this one, I'm coming from physics because it's true, of course, in a very general sense, there is a dichotomy between two behaviors, namely, either you have a localization of the eigenvectors, so the eigenvectors they like make a huge peak somewhere, and then you expect that the associated eigenvalues they are distributed like a Poisson point process. So there is no, in fact, interaction between the eigenvalues. Or the other thing that can happen, sorry, I went too far, is that you have delocalization of the eigenvectors. So they took now the whole space, the whole size of the segment is full with the L2 mass of the eigenvectors. And the associated eigenvalues, then you expect that there is some repulsion between the points. And Cyril has presented five regimes, and I just recall two. What Cyril has presented is that when E is much smaller than the size of the box, so E is the point where you zoom in the eigenvalues, then the eigenvalues are distributed like a Poisson point process, and the eigenfunction associated to those eigenvalues are localized. And in fact, we have information about the localization next. And when now we take E, which is very large and which is exactly of the order of the size of the box, then the eigenvalues now have some repulsion indeed and are delocalized. So it satisfies the dichotomy I just presented. And so we will focus now on the critical case, what we call critical case, so when E is of order n. And if we have time, we'll see, I will talk a bit about the localized setting, but the main goal is to talk about this critical case. So we zoom around energy of order n. So as I said, we need we look at the eigenvalues, and we need a scaling factor here to see only a finite number of them around it. And we look at eigenfunctions. And eigenfunctions, I made a drawing. So they oscillate a lot. And so you have to imagine that it looks like this thing. And so in fact, the first information we keep about the eigenfunction is this associated probability measure. So we rescale the space here. So instead of having a function from minus L/2, we now have a random probability measure on the finite segment of size 1 here. And I did the rescaling. The eigenfunctions are L2 normalized, so I put L here so that indeed we have a probability measure on this size. Okay, and that's what we will study. And so we look at a point process whose first component is the eigenvalue rescaled around E rescale, and the second component is this probability measure, random probability measure coming from the eigenfunction. And the result is that it converges towards a non-trivial object, a random point process, which is characterized by coupled diffusions. And so let's first look at the first component here. So the eigenvalues, okay? Then the limiting eigenvalue point process is a point process that was already introduced in the literature by Krzyzewski, Walko, and Dirac in 2012, and which is called the SCH-tau point process. It's a process which has repulsion between the points. So in fact, in this paper, they prove some estimates showing that indeed there is repulsion between the points. So it's not at all like a Poisson process, totally different. And I will maybe say a bit more, but there is a nice characterization thanks to using hyperbolic geometry. But what you have to remember is that there is repulsion between the points, and there is also the parameter tau. Sorry, I didn't say. So we rescale E exactly so that E over L is converges towards the tau. So tau is coming from this thing. And for the eigenvectors, in fact, they have a very nice shape that Cyril mentioned. They behave like the exponential of Brownian motion plus a drift around a uniform point that you choose around on your set minus L/2, L/2. So this was conjecture for this model by Rifkin and Dirac, who proved a similar behavior for a discrete model. And here what you have to notice as well is that there is an interaction between the eigenvectors. So it's not at all like a Poisson point process here. So they see each other somehow, those eigenvectors. But it's difficult to say something precise about this. And so to come back to the behavior of the eigenvectors, I made also some drawing. So here you have your initial eigenvectors rescaled, okay? And so what does it look like? It looks like, so again, you take U, uniform point around on minus L/2, L/2 on the segment. And then it's simply, as I said, exponential of a drift here, a linear drift like this, around starting from around U here. And you see that there is the factor tau which appears here. So the more tau, when tau is large, it becomes more concentrated, the eigenvector somehow, which is coherent with the scaling that we have. And here you have, again, a Brownian motion, which is not at all the same Brownian motion as the one defining the operator, And so you instead of having a deterministic shape, you have here really a random shape. So it's still random. It's the shape of the eigenvector.
Sorry, what is tau? Tau.
Tau is E over L. So it's how much E is close to.
Thank you.
Okay, so that's so it's only this. So it's the only parameter that remains here. And as I said, it's nice because it's supposed to be a universal shape. In fact, it's conjectured by Hamiltonian and Dirac to rise in mainly one-dimensional model, which are transitioning from localized to delocalized. And Cyril mentioned that its shape starts to appear, in fact, in the localized region when you zoom near the localization point. So imagine that you have your eigenvector now, which is on minus L over 2. So here is just a slide about the localized case. So really, you take, there is a random point, ui, which is still uniform on minus L over 2, where when you zoom near this point here, of the right scaling, the scaling is E, you have this exact same shape. So it's a nice, a very nice feature of this model that there is the same shape appearing from localized to delocalized. But now we have seen that the eigenvalues and the eigenvectors, they converge towards non-trivial objects. So you can wonder if we can improve our convergence and have a convergence at the level of operators. And is there an operator appearing at the limit, a non-trivial operator, because it has it would have those eigenvalues, so with eigenvalues which are recursive point, which will be the eigenvalues of the SCH tau point process, and those eigenvectors which have this shape.
Sorry, in the previous slides there was a formula for localized eigenfunction, and there is no tau in this formula. It was some constant. How it is possible? It is not normalized.
Yes. Yeah, it really comes from so it's normalized. I didn't put it here, but here you really zoom around the point ui here, and when you zoom in the correct way, you see this shape appearing, and indeed there is no tau here. So because you zoom exactly because the zoom is included here. But if you replace, if E was of the order, you see, it's just a matter of zooming in the correct way. If I don't know if it's if you understand now.
Thank you.
Yeah. Okay. But indeed, in fact, when you want to, you could go from. I mean, yeah, it's just yeah. Okay. And indeed, it converges towards a non-trivial random operator. So if you rescale it around E, and you have to make a unitary unitary conjugation, then it converges towards this operator. So first thing you may wonder is that, oh, this operator acts on L2 functions, but which are R2 values, and not real valued. So there is a dimension that pops in, and I will explain why. It comes from this unitary change here. It's non-trivial. But so let's look at this limiting operator. So it has a very nice form. It's again a differential operator, and we can prove that it's self-adjoint. The factor square root of 2 appears here. The factor tau, sorry, appears here. So again, it's E over L. And here we have dB, dW1, and dW2, which are white noises, and they are all independent. Okay, 3 independent white noises. So it's kind of strange. Again, we started with 1 white noise, and we get 3 in the limit. Okay.
So it is the limit when L tends to infinity. It tends to infinity, yes.
When E goes to infinity at the same time as L, and when E over L goes to tau. Indeed.
Okay, thank you.
And when you rescale, of course, your operator so that it acts on now function on, I put it on 0, 1 here, or minus L over 2, L over 2.
Thank you.
And so this convergence, I didn't say, but it holds in the strong resolvent sense. And you cannot hope to improve to norm resolvent sense because it does not converge in norm resolvent sense. And so that's a bit an issue because the strong resolvent sense is not so strong, in fact, despite its name. For example, it does not imply that there is convergence of the eigenvalues and eigenvectors. Some of them could vanish at the limit. But so but in fact, we prove also that there is convergence law of the eigenvalues and eigenvectors of the operator HL towards the limiting operator. So there is no spectrum vanishing or things like this. But it's something that we have to state to write because the strong resolvent sense was not able to deal with this issue. And such a form of operator was appearing in the works of Edelman and Sutton, in fact, as a conjecture for the bulk of some tridiagonal matrices. And so that's nice that we end up with this form. So some remarks. So the limiting operator, I told you, it's a bit strange. It acts on R2 valued functions. So it means that we enlarge the initial space. Right, so we had just a R valued function, and so we enlarge it, we add some information so that it's now on R2. So the transformation is non-trivial. And another remark is that we have some issues for defining this operator, in fact, a bit like the initial one, because we multiply again some function by white nurses. Except that in this case, it's a bit more annoying because we cannot somehow subtract, as Cyril has shown, we cannot have a nice, I don't know, trick to deal with this. And so an elegant way to define it is in fact to use Dirac operators, which appeared recently in the work of Valco and Virag, who they wrote an article about the operators that appears at the limit of mainly random matrix models. And so the Dirac operators, it's easy to define them. And so the idea is to put our operator to change it unitarily so that it's on this form. I will explain a bit more. And our approach can easily, probably, let's say, be extended to other models. So the bulk of tridiagonal matrices or other differential operators. So it's a bit robust. Okay, so how does it work to obtain this operator? So we need to rescale our operator around the energy E. So we both recenter and rescale the function so that instead of acting on L2 of minus L over 2, L over 2, you shrink and they act on L2 of minus 1/2, 1/2. Okay, so that's the first basic thing to say, to do. And when you do that, you quickly realize that you will have a big problem, an issue, because the eigenfunction, I made some drawings, they in fact oscillate a lot. They oscillate of order E at the power 3/2. And so it's impossible for them to have a limit as functions. They really oscillate. And so we need to remove those oscillations to have a function. And that's what we will do to. And in order to remove the oscillations, nice way to do that is to consider both the eigenfunction and its derivative. So that's where the R2 space comes from, that in fact, instead of looking at the operator on the function, now you look at its action on the function and its derivative. And so we will embed our operator into an Hilbert space of the type L2 of R, where R is a symmetric 2x2 matrix, and that's the definition of the Hilbert space. And now, so you have those things. I told you, you have to remove the oscillations. So let's say that you know that the oscillations are of order E prime, where E prime, I told you, it's basically E at the power 3/2. Okay.
Sorry, in the previous formula, there was F, R, F. What is R? In the previous formula, previous slide.
I didn't define it. I just told you it's a symmetric 2x2 matrix. Okay, in this case, I mean, we will choose a specific R for our problem, and it will appear. I will show you. It was just to show the form of the Hilbert space, but I didn't indeed state now yet what is R, but I will tell you later.
Thank you.
And so the operator, so imagine now you have your eigenfunction, it oscillates a lot, and you know that in fact it oscillates like E prime. So E prime is of order E at the power 3/2. So let's say that, so if you take a vector and you want to remove E prime somehow, you can just multiply by this rotation matrix, right? So you take this rotation matrix, you multiply by your vector, and then it gives you, it simply removes this E prime from the face, E prime times T, if it's the order of magnitude, okay? And that's what we will do. So we take a solution of the differential equation, which corresponds to the eigenvalue equation, okay? So HL of phi lambda is equal to lambda phi lambda. We rescale, and then what we do, we rescale, I told you it oscillates a lot, so we unrotate by this rotation matrix, and it gives a vector. And now I want to say, okay, what does it look like, this vector? And it turns out that this vector is a solution of this SD. Okay, it does not look maybe very nice, but it's not so complicated. So you see, we have, okay, it's a solution of this SD. So what do we have in this SD? We have a matrix R E prime, which is in fact corresponds to the R E, and that's a matrix R that I was mentioning. So it will define an operator that will act on L2 of R E prime. Okay. And R E prime is this matrix, oscillating matrix, that comes from this rotation C E prime. Okay, so there is this that appears here, and there are some red and blue and orange things here, which are coming from our potential. So BL is the rescaled potential, and W1 and W2 are the rescaled potential, but somehow multiplied by oscillating cos and sine. Okay, and so that's what's up here. So it's just a computation somehow. So, but now you have this computation, you see that it's this thing is very similar to the limiting eigenvalue equation coming from the limiting operator. The limiting operator was really writing this way with a factor 2. So I multiply everything by, I divide everything by 2. But this is the eigenvalue equation of the limiting operator. So you see the similarity, and what's happening is that in fact those three Brownian motions here, they become independent at the limit, because here the oscillation comes to tends to infinity. Okay, so that's a vague explanation of why this operator appears at the limit. Now I would like to make the link with the operators of Valco and Dirac. First, because we use them, in fact, in our article to define properly our operator, but also because it's a very nice theory, in fact. And that was really an inspiration for us. So what's a Dirac operator? it's a differential self-adjoint operator, which was in this very simple form. Okay, so to a function, which is R2 valued, you associate R of t minus 1. R of t is simply 2 by 2 symmetric positive matrix of determinant 1. Okay, anything you want. And then there is J. J is this matrix. And then you differentiate with respect to t. Okay, so that it's a very simple differential operator with only one. You differentiate only on here. Okay, and it's a self-adjoint operator on, in fact, L2 of R. So again, this R is really linked to the 0, the one I defined previously. And R, I told you it's a symmetric 2 by 2 matrix, which is non-negative, positive, sorry. And so in fact, you, with determinant 1, so you can always decompose it in this way. So there exists a matrix X, which writes in this way, such that you can write R into this form, okay? It's, I don't know if it has a name, but it's a natural decomposition of this symmetric matrix. So I do that. And now I want to know about the spectral properties of a Dirac operator. So I look at the eigenvalue equation. And a very nice fact is that if you look at, so f really is a R2 valued function, so it's f1, f2. If I look at the quotient of the two, so f1 over f2, then it follows a hyperbolic rotation at speed lambda. Lambda is really this factor here. Lambda dt, I told about what's happening really at time t. So hyperbolic rotation around a point here, which is x plus iy. X and y appears here in the decomposition of R in H. So I made a drawing. I don't know if it's very helpful, but so you have the hyperbolic geometry in H, okay, and in fact, what's happening for your eigenfunction is that really, or not your eigenfunction, but just in fact a solution of the eigenvalue equation. So it really follows an hyperbolic rotation. So f1 over f2 is a real point, okay? So it evolves on the boundary of H, where H is the upper half plane. And so it evolves like this, and it can hit plus infinity, in fact. And so it evolves like a hyperbolic rotation. Okay, you make an hyperbolic rotation around this point, which evolves in time. And okay, and let me say just a bit more about this. So in fact, using this hyperbolic interpretation, which is a nice geometric way to see that, to see the operator somehow, how the solution of the eigenvalue equation evolves. It's a nice way to represent that. Valco and Dirac really proved a lot of things about the eigenvalues of the operator. So you can, like, really understanding this motion, really, f1 over f2, it can tell you a lot about the eigenvalue point process of the operator. And in particular, I told you for some specific case, we have repulsion between the points, etc. And it can be really studied using this interpretation. And what's the link between our operator and an operator of this type? So for the moment, I just introduced Dirac operator and a nice hyperbolic way to see the Dirac operator, okay, which was really, I think, seen by Valco and Dirac and used by Valco and Dirac. And now if we take our random operator, we can unitarily change it so that it becomes a Dirac operator associated to a very simple path. So recall that there is this path here that encodes the matrix R. Very simple path, which is a hyperbolic Brownian motion of variance 2 over 2. Okay, So if you want to understand the evolution of solution of the eigenvalue equation, you just have to make an hyperbolic rotation with respect to this hyperbolic, where the center of your rotation is this hyperbolic Brownian motion. Okay, so that's just what I wanted to say. And okay, just about this result, unitary map is random, so it's non-trivial. And the boundary conditions are complicated, but they are explicit. Okay, so I see that I have still 10 minutes. So I will now, if you were a bit lost by hyperbolic geometry, you can come back. And I will just give some ideas for the proofs in the localized regime. So how can you prove localization of the eigenvectors in the localized regime? So now we take E, which is not of order L, but much smaller than L. Okay, so think E of order 1. Okay, that does not depend on the size of the box. And you want to see that the eigenfunctions are localized. So you look at the eigenvalue equation. And the first idea is that instead of, so you have Dirichlet boundary conditions. Your eigenvalues must start from 0 and end at 0. And now let's say that you look at the solution of the eigenvalue equation, but only with the starting initial constraint. So it starts from 0, and you do not put any condition on the ending point. So for all lambda, then you have a unique solution up to a scaling. And the couple lambda phi lambda is an eigenvalue eigenvector when your ending condition is satisfied. And what you have to keep in mind is that this phi lambda here is much easier to analyze than the solution of the eigenvalue problem when you really want both of your condition, initial and ending condition to be satisfied. Okay, it's because in this case, when you want both of your conditions to be satisfied, lambda is random and it depends on the whole potential, and so it's much more difficult. And so the idea is that we will try to use this phi lambda to understand some information about the eigenfunction, the proper eigenfunction, when lambda is random. Like here, lambda is fixed, and for an eigenvalue, an eigenfunction, sorry, lambda is random. And of course, you could do the reverse, like fix the ending condition at 0 and solve the equation backward. And this gives phi lambda hat. Okay, there is always a unique solution, etc. And you have an eigenvalue eigenvector when the starting condition is satisfied. And the key idea is to use both. And we will use the forward solution on some time interval until a well-chosen point u here, and the backward equation for the rest here. So from L/2 to u. And so we look at the concatenation of the two. If lambda is an eigenvalue, of course, it changes nothing. You are back. It's continuous, everything is perfect. And the fact is that if lambda is close to an eigenvalue, it will be close to an eigenvector if u corresponds to the maximum of your eigenvector. So it's written as a fact, but there is a formula that really proves this fact. And why does it help? It helps a lot because, as I told you, it's much easier to analyze phi lambda and phi hat lambda because they are solution of an ODE. So you can use this this work on the solution of the ODE and transfer it to the eigen functions. And so here is a big formula that really explains this fact here. So we called it Goldscheid-Molchanov-Pastur formula, and that's a proposition that we prove with Cyril to prove a localization in our case. And what does it say? Well, you see on the left, you have some observable of the eigenvalues and the associated eigenvectors. So this is some function. G is any function you prefer. And so it gives you some information about the eigenvalue and the associated eigenvector. So that's the left-hand side. And on the right-hand side, you have something very nice. Lambda is no longer an eigenvalue. It's an element of R here. So you integrate over all lambda. And here, what you have is the expectation of the same function G, but lambda, so I told you, is an element of R. And here is exactly the concatenation I told you about. Okay, so if you have information about that, you can transfer it and understand something about your eigenvalue and eigenfunction. And that's the key idea. And of course, now you have to analyze this formula. And the key idea is that indeed, it will make a lot of, it will be relevant here, the expectation will be relevant and will be large when U is correspond exactly to the argmax, is close to the argmax of the eigen of the function phi lambda somehow. So that's why that's the explanation of this fact. Okay, and there is some work, of course, here to be done to understand p lambda of theta, which is a transition probability of some phase function, which is the argument of this. Okay, so I think I will stop now. I still have 5 minutes, so I don't know, maybe you want to know, I don't know, either I stop or I tell you a strategy to prove convergence towards the Poisson point process. I don't know. What do you suggest? I can also stop if you are tired.
So as you feel like this, maybe my question is, what is the strategy for the Poisson point process?
Yeah, thank you. Very good question, and I have some slides about this. Okay, so in fact, so I gave you some arguments to prove localization. I told you this nice formula was gave us some localization, gave us localization in the eigenvectors. And now you can wonder, okay, but how do we indeed have the Poisson point process for the eigenvalues associated to those eigenvectors? And here is a general strategy that is very well known and that has been applied many times. But to transfer, when you have information that your eigenvectors are localized, how you can prove that you have a Poisson point process for the associated eigenvalues, okay? So that's somehow that for the dichotomy, that's when you have already information about the eigenvectors and you want to know something about the eigenvalues. So the strategy is the following. So recall that we are interested in an interval delta of the eigenvalues, which is around E here. So I rescale things so that, again, we have a finite number of eigenvalues around the delta, even in the large L limit. And n of delta is the number of eigenvalues in this delta. And so here is the eigenvalues. And on the side of the eigenvectors, you will divide minus L over 2 into small boxes, which are of the same length. Okay. And now you know that your eigenvectors are localized. So they put all their mass somehow on only one of the box BI. That's an information that you have. And so what you can say that your eigenvectors, vector here, which is really only in one box BI, it has almost Dirichlet boundary conditions here. Okay, it's very close. So it's very close to an eigenvector, which is corresponding to the same operator, but restricted on the box BI. But now you can say, okay, but all those boxes, we are dealing with the white noise here. So all what's happening in the box B1 is totally independent of what's happening on the box B2, and all those, in fact, are IIG. And so if we would like to, let me summarize. When you have an eigenvalue, you look at the associated eigenvectors, and I told you it corresponds to, in fact, nearly an eigenvalue of the restricted problem on the box BI here. So the number of total number of eigenvalues here in the O box delta corresponds to the sum over all those eigenvalue problems restricted on each box. Okay. And so you have n of delta, which is the sum of a lot of IIG realization. But now delta is is small. BI is small here. So in fact, what will occur is that either you will have one eigenvalue or zero, but you cannot have two, in fact. So in fact, you have the sum here of Bernoulli random variables, independent of certain mean. And what I said is that, okay, you cannot have 2 points here. Okay, it turns to zero. If you have those three information, then it's easy to derive that indeed you have a Poisson random variable here. And so that's the general strategy. But of course, what is hidden, so this part is, is doable, but what is hard, in fact, is this last thing. It took us a lot of work to prove that indeed you cannot have 2 points for this restricted problem, more than 2 eigenvalues okay, so that was a difficult issue here. Okay, so let me thank you. Okay,
thank you very much,
for your attention.
So are there any questions?
Sorry, I want to ask 2 questions. First is about your operator. You have written the formula for operator and then told it is not well defined. Why it is not well defined? And secondly, how it was connected with hyperbolic rotation. In what sense? Yes. First one is one that is not well defined. Before it was before.
Why it's not well defined as a limiting operator, right?
Well, in the operator, yes. The operator, you say, is not well defined. In what sense it was? It was before. It was written. Yes.
It's not well defined because here you have white noises.
Yes.
So same issue as before. You multiply a function f, which is supposed to be in L2, by some white noise. So you have to. So it's really the same issue as for HL, except it's more complex because now you have linear combinations of those things. So you cannot really have a nice, how to say, like before we were able to subtract somehow to make an IPP and deal with this issue. But here it's more complex, in fact.
Thank you.
Why, so it's really the same issue. You multiply a function by something which is not a function. And it's not in L2.
Thank you.
And
then how it was connected with hyperbolic rotation. You say that operator is connected with hyperbolic.
About this thing, this question, it's because it's connected to this operator, an operator of this type. So I told you if you unitarily change your operator, you can fall to some Dirac operator of this form. Okay. Okay, instead of, so you can conjugate it and really get something like this. And now I told you that generally, when you have a Dirac operator, it's connected to hyperbolic geometry, because if you look at the eigenvalue equation, so this, the eigenvalue equation, then it follows an hyperbolic rotation, around a point that is encoded into your matrix R here. That's and yeah.
Thank you. No, it was later. It was about another operator later. Next problem, next page, that something is connected with hyperbolic rotation. Yes. No. Okay, thank you. And then the page, it was also the same. Yes.
Yeah, so that's the same. I just made a drawing of hyperbolic rotation. But here we look at the action of the hyperbolic rotation on the boundary, because F1 over F2 is on the boundary of H. But I made some drawing here to say that the other points also move.
Yes, there was some operator connected with white noise. Again, it was told that it is connected with hyperbolic rotation, but in the white noise case, it wasn't very clear. In the next page, probably.
Next page.
Probably next page. Yes. How the Dirac operator, this operator is unitary equivalent to Dirac operator associated to hyperbolic Brownian motion.
Yeah.
In the sense, Dirac operator, yes.
In the sense that this path follows a hyperbolic Brownian motion. Now we have random operators. So in fact, the randomness is really in the function R, the function R defining here's the Dirac operator, okay, this function R. And this function R, if you write it in this way, and X and Y here are random, and if X and plus IY follow a hyperbolic Brownian motion, then it's really the operator, and it corresponds to a unitarily transformation of all operator.
Thank you.
Thank you for your question.
Andrew?
Yes, thank you. It was excellent presentations, both basically 3 questions, but I hope not to steal the place to anybody else. Firstly, related to random matrices that you mentioned, related to this article of Dirac and co-author, could this, I mean, where is the intuition? What kind of random matrices this relates to? Could this be directly related? Is this related to general beta ensembles? I assume. I briefly checked the article probably. And how would there be an intuition to direct random matrices connected to this Anderson Hamiltonian? And second and third, very short ones. Second one, I think that in one of your recent articles, you use also Maillard derivatives, so stochastic derivatives. Could anything change if in the derivative part, if in the eigenvalue equation, would you use these stochastic derivatives instead of the regular ones? And thirdly, as to the last part, to the question of Avelio for the localization part, where you had this division into boxes, how do you define the number of boxes? I think this was this n of delta, but it was going too quickly. So how is this number of boxes defined? Could anything be done here? Thanks. I hope not to steal too much place.
Thank you. Okay, I will try to remember all your questions. So yeah, for your first question, indeed, it's related to the beta ensembles. And in fact, any tridiagonal matrix. So what Valco and Dirac have done, part of their work, that they have shown that for beta ensembles, and they use the tridiagonal representation to study beta ensembles. And those tridiagonal representation really can be seen a bit like as a discrete random Schrödinger operator somehow, because it's just tridiagonal, so you can imagine that there is Laplacian plus some noise, or at least okay, I'm going a bit fast, but yes, so indeed the link is for beta ensembles, but also tridiagonal matrix, which really corresponds to, in fact, the more precise thing would be a tridiagonal matrix, which really corresponds to the discretization of our operator.
Is there also a link to Edelman and Dumitriu, this article on triagonal and general beta ensembles? Probably there is connection.
Because Valco and Dirac really use this tridiagonal representation.
Okay.
So the key is indeed to have a tridiagonal matrix.
Okay.
And then you can interpret it somehow as a differential operator, at least, okay, that's true for some, but not exactly, but you can understand still what's happening, and that's how they make this connection, because they realize first, in fact, that the eigenvalue point process of the bulk of beta ensembles follow some nice hyperbolic motion. So they realize that first, and then they define indeed the operator corresponding to this hyperbolic corresponding to this hyperbolic rotation.
Of course. Yes.
Okay. So about your second question.
Yes, the stochastic derivatives.
Sorry?
Stochastic derivatives. What would change if you would use, say, in your usage of the derivations in the eigenvalue equation, Maillard derivatives, say?
Yeah, so about this part, okay, it's not something I mentioned at all during the talk. Okay, we use Maillard to have some okay, so maybe to have some information about the phase function here and its convergence towards equilibrium.
Okay.
Okay, so that's and what did you want more specifically to know?
No, basically, it was just a question if this could be used in any way to replace the derivations that you have. Would this make any sense? Because you used Brownian motion on the F, and it could make sense to use stochastic derivatives there at least.
So could you repeat? I didn't get it.
Basically, could also stochastic derivatives be used instead of the general derivations? Maybe, okay.
You mean for the critical model, or?
Yes, for the general model in the eigenvalue equation.
Okay. You mean
with the Brownian.
So that the operator makes sense, or I don't know. At least for this model, we don't need to use at all. We have I mean SGs, and we don't use Maillard for the critical part.
Okay. Thanks.
And your third question?
It was just how do they determine the number of boxes in the localization part?
So, it's indeed it's important. We have to choose it carefully so that, okay, what we need really is to have an infinite number of boxes, and we have to choose it carefully so that indeed it's true that the eigenvector is really only on one box. So if it's too large, it would not be true. But we just need an infinite number of boxes, I think, at least for the, okay. Okay, we need to choose it carefully, but the number of boxes. So we cannot be in anything. We have to choose the length properly to have the information that we need.
Okay, thank
so
you.
It's something like, I don't know, we have log L of boxes or something like this. But okay, but it's an important technical point. We need to choose carefully the number of boxes. But the argument here does not depend on the number of boxes here, you see. So it's quite general, but then when you want to really go into details and to have really the information, then that's when you need to be more precise about the number of boxes.
Okay, thank you. Thanks.
Thank you for your questions.
Thank you. So are there any other questions? So if not, I propose that we unmute ourselves and that we give a big round of applause for Laure and Cyril. Thank you very much. It was really fun today.
Thank you for the invitation again.
We should stop recording.
Yeah.